program description. It has 8 pages. And the basic idea there is that we want you to implement a neural network. And I haven't taught you how what neural network is. We'll do that next week and later next week. So a lot of things that you need in this assignment are not taught yet. You can go out and start working on it. But there are some sort of pre-processing phases that you can start doing, which are also great. So things like sampling, that just gives you a feel of what you can find on it, right? The general idea behind this assignment is for you to get a sense of how to solve a real problem. How to solve a real problem using machine learning from the scratch. We will use some packages, but most of it would be done from scratch. There is one part of the assignment which is only for graduate students, so 574, which is using doing a little bit of deep learning, so using a library called TensorFlow to do the analysis. The 474 students are welcome to try that for extra credit. So if you do, you get 20 points more. Otherwise, you don't have to. So undergraduates, and it's all in this file, everything. Right? So all these files that are provided to you, you will find it learned. So there is data, there is some script in which we have already written some code, and you just need to fill out the rest of it. There's one script with the deep learning part that's not up yet, that I'll add later. But anyway, those things you'll be looking at in a couple of weeks. Okay? So the first thing you want to do when you go back is to start playing with this data. To make that easier, I have, if we go to our machine learning course page, I have one notebook. This called Programming Planning 1.0. Why? So this is just to understand the data. Okay? This has routines to go with the data and play around with it. So let me just go back and try this out. This will also be a introduction to the notebook. Some of you might not be familiar with that. These are just sort of browser-based way of writing Python and interacting with Python. Or instead of writing scripts and working on the command line, this lets you do it on the browser. It's quite nice. Right? So go through it. The basic idea is that we pick some data, which is each data point is an image of a handwritten digit. Right? So these, for example, these are all the 9 digits, or some of the 9 digits. And the task is to create a classifier which can distinguish between these digits. So if I give you a new image, you need to tell us if it is 1 or 0 to 9. Right? So there's a variability in how these bigger of handwritten, right? And so it's not like all the digits are exactly the same. Here's the truth. Anyway, there is variability across the digits. Right? So that's one part. For the graduate part, you need to look at a little more challenging data. What you will see here is, once you write your neural network in a nice way, you will get accuracies of 96% and 97%. I mean, the data is fairly easy. But it's a standard benchmark data set that we use to understand the performance of the algorithm. Another one is which we got from this another website. This is Faces. Okay? Faces of celebrities. Only celebrities. And there are a lot of features associated with these. A lot of concepts that you can learn. The concept that we want you to learn is the ability to distinguish between images with glasses and images with no glasses. Alright? So here are some sample images in which the person is not wearing a glasses, in all of these they are. Right? And your job is to learn to distinguish between this concept, right? And what you will find is that a simple neural network that would give you 96% accuracy in digit space will not work very well together. So that is the kind of thing that I've been trying to tell you is that different problems will have different complexity. Right? And then what we can see is that if you make the neural network more complex, which is called a deep neural network, you will get improved performance. So those are the things that you have to try. Okay? So without knowing neural networks, the first thing you can do to get started on this assignment is to data, start playing, like understand. Any questions so far? Yeah. How is it great? So, okay. So if you look at the whole assignment description, right? At the end, we ask you things to submit. So you need to submit your code, which is we will give you the function skeleton. All you need to do is fill the logic inside, right? Then what you will do is you will test each function with some script. So if your function gives us the answer that we expect, then you get it. There's also one part where you need to do some analysis. So that will go in a project report. In the analysis, you need to understand, okay, how does the performance change and certain parameters of that will change. So we have to do that analysis, and there are points for that as well. So you will see all the grading scheme pretty clearly laid out here. So there are different functions that you need to populate, and if your function is working the way we expect, then so on. And at the end, but your entire method should also be accurate. There are some points for that. And then, of course, for the graduate part, there is some extra points for analyzing that case. Oh, I mean, you won't be able to go beyond 95 or 95%. That's sort of the maximum anybody can get on that data set. So, if you I mean, this is all test data, so that's sort of the height. If you do anything wrong, you will see you get poor accuracy. So there is no middle ground. So if you get it correct, you will get good accuracy. Any other question? Yeah. Okay. I think it will be a good question. So the question is how will the extra credit be applied? So actually get extra points for the assignment. So the assignment is worth 10% of the entire grade. So if you do everything correctly, you get 11. It would help in offsetting some other numbers. Right? Any other question? Alright, now let's get started with the main part of today's lecture, which is continuing with Winnow. Right? So in last class, we were trying to understand these mistake bounds, right? And the point that we sort of stopped at was that for any type of concept, or actually for any concept class, it could be disjunctive, we saw there is one general algorithm for halving algorithm. And if you analyze it, its mistake bound is log of the size of the concept space, right? Because at every step, it has your version space and it reaches the right action. So that kind of is a bound that we have for any algorithm, right? That's why I used this figure. We said that for a certain concept class, the optimal, the best algorithm first performance, right? That's this. Can be bounded by halving that log C. And there is another algorithm for randomized halving that we will not look at this time. That gives you a slightly more tighter bound. So the whole area of learning theory, computational learning theory, they are trying to do things like this. So they are trying to get tighter and tighter bounds for performance of algorithms. Right? But we are going to just stop at this. So what we see is that log of the size of the concept space is a bound that we get. That means that you cannot have any algorithm. I'm sorry. So what that means is that there is at least one algorithm, which in worst case will make these mistakes to learn the concept. Right? However, another point that I made last time was that this algorithm, given that it sort of starts with the entire concept space and tries to bring it down, is not very efficient to work. Right? It's not. You cannot apply it. So the next question was: are there any efficient algorithms which could give us bounds like these, but are more easy to implement? And the answer to that was that in general, they are not. Like for any concept class, it's hard to come up with one answer. But, and that is why the whole area of machine learning has so many algorithms, right? So what people have done is for special types of concept classes, right? They have come up with algorithms that work very well there. So what we will see today is one aspect which makes an assumption about the concept class. So instead of looking at any concept class, it works with one particular type of concept class. And then we will show that that average also can work in log of the size of the concept class. Right? So that concept class is what we call K-monotone disjunction, right? And the algorithm that we will use to learn is called disjunction. And we will not really go into the proof that much because that sort of, it takes, it's beyond the scope of this class. But when you do the gradients problem for this week, there's one part that will help you understand those forms a little bit, right? And after that, you get something very interested. That is more of a thing that's useful for someone who wants to go into the learning theory research. And it's very interesting. Everything is interesting, but it's not something that everybody wants to do. Okay? So the first thing you want to understand is what is the concept class that we are trying to learn. This is no longer a conjunctive concept class. Now it is our monotone disjunction of at most k way, or what we call at most k monotone disjunction. And last time we kind of looked at it, right? So the idea is that the concepts are of a certain type, of a certain format, right? They are expressed as a disjunction, as a logical or of some of the attributes or some of the features, and only k, at most k are allowed. Okay, let's go back. Okay. So what is a k monotone disjunction? That's what we are going to define today. And the next thing is what we're going to define what is an at most k monotone disjunction. So k monotone disjunction is a concept that can be expressed as a logical or of some of the attributes. So example, if you recall the example of the skew, right? So one possible concept could be circular or dark. So any tumor that is circular or any tumor that is dark is disjunction. Right? That could be a concept. So it's going to call all those tumors as if you want to contrast this with conjunctive concept, conjunctive concept typically has circular and right? Both attributes. But here only one can be true, or both cases. Another constraint that we put on these is the notion of monotonicity. What that means is that the features, right? You can express the features as true or false. So in our example, we've been using the axiosemantic name like circular, dark, and so on. But you could express each feature as true or false, right? So, and then you can assign something. Circular means true and oval false. So monotone disjunction. So now what we can do is we can express each feature as x1, x2, x3, xd, and then each feature can take two values. It could be either true, so it could be true or false. And just for notation, sometimes we also write this. It could be x1 or not. Right? So then each disjunction can be written as this: x1 or x3 or x6. This is the same as this. Monotonicity means that we are only going to allow positive values of the feature. So that means x1 or x3 or x6 is fine, but x1 or x or x3 is not fine. That's not a monotonic system. Why do we do that? That's more to just keep our analysis. I know that this kind of restricts the type of concept that we have, right? But the idea is that to define the concept class and then use the analysis. So this is going to be our concept class. Then there's the notion of K. K means that you can have K features here. So this is like 3 features. Okay? At most K means you can have K or less. You can have, so let's say we want to define speed. monotone, at most 3 more disjunctions. So let's see, some of the valid disjunctions of at most 3 will be x1 or x4 or x6, x1 or x5, just x6, right, or nothing at all. These are all valid, these are all valid. Some of the invalid ones would be x1 or x4 or x5 or x6. This is not correct, this is not at most 3. X1 or x4 are not monotone, and x1 and x3 and x4. Okay. And this is not disjunct. Okay. So these are the types of concepts that you would like to learn. Yes. So here we are still assuming that all of our features are binary. This algorithm is only meant for binary. So the question was, what if it takes 3 values, and we are not going to handle that in this algorithm. Any other questions? Well, so there's a definition of these monotone disjunctions, right? So if you look at this one, the reason this is invalid, it is not a 3 monotone disjunction, is because it has 4 units. Just a definition, right? The reason this is not a valid 3 monotone disjunction, or at most 3, is because it has a negative. It allows a negative feature type. We are only going to allow a positive feature type. And this one is not, because it has a conjunction. Okay. And then we also look at how to count these, right? So, and it's easy to count these, right? So if you have, so let's first do how many exactly k monotone disjunctions you can have. That is easy. So how many k monotone? Exactly. So that means that you have d features, and you have to pick k out, right? You can do that in d choose k. Right? Then somebody asks how many at most k. Then that would just be a summation. So you can either have none, so that's just one way. That's d choose k. You can have one, which would be d ways, and so on, and d. Right? This is just combinatorial. Any question about that now? Okay. Now, and then you can also like mathematically sort of sum it up, and it turns out this will be nearly or equal to. So this is our concept class size, right? So the log of this will be nearly equal to theta. It is log a here, log the log of this, and you can get a general sense of this, right? Because if you let this sort of go on till d, this would be 2 power d. That means c will be kind of d, a will become d, and then it's all the same thing, right? So yeah, so this is the idea. So this is the size of the space. The reason I'm expressing it in this way is because we know that halving algorithm can learn a monotone disjunction in log of c with log c mistake, right? So this we have already seen in the math. Which means, and log c is this, which means that it is equivalent to k log 2d. Right? So that is easy, but of course, that halving algorithm is not a very good algorithm apply. So now we're going to look at another algorithm called Winnow. And we will see that that algorithm can also learn these concepts with these tools. You will not see that, but that's what we will do, right? Okay, so this is our first step towards some real machine learning algorithms. It's time to come out of our introduction sandbox, right? We're going to the real school here. Alright. So the first thing we want to talk about is linearly separable constants. Okay? So this theta is the big theta notation in algorithms. You must have that. So this basically means it's sort of it's a constant of this. It's not exactly this. It's a constant. It's a big O, big theta, that kind of thing. So you can, just for this class, nearly equal to don't be exact. Alright? Okay. Alright, so let's go back to this. So the way Winnow works is that it is an algorithm which tries to draw a line between points. Okay, so it's a geometric algorithm. So what that does is that it sort of puts your points on a coordinate space, right? Like this. So think of this as your two-dimensional space with two axes, x1 and x2, right? And each of your points, because each one of your points is a binary point with two features. Let's say it has only two features. So you can only have 4 points, right? You can have 0, 0, 0, 1, 1, 0, and 1, 1. So you can represent all 4 of them like this, right? If you have a 3-dimensional space, then your points will be if your data objects are represented using 3 binary features, you can show it in a 3-dimensional space and 4-dimensional and so on, right? But here, just for illustration, we are assuming our data is in 2-dimensional space. That means you can only have 4. Okay. Now, the target concept is going to color these, right? It's going to call some of them as positive and some of them as negative. And what we can show easily is that if the concept is disjunctive, K-monotone disjunctive, then you can always draw a line such that the positive points will be on one side of the line and negative points will be on another side. Okay, so let me give you a quick illustration. So this is sort of very important even for future. Let's say we are representing our data. Our data is x1, x2, x1, x2, bar, x1, right? So you can always represent this data in 2-dimensional space where one axis is in x1, x2. So x1, x2 will be both are 1, and this one will be I'll call it x1, x2. This one is x1 bar, x1, x2 bar, x2 is 0, and this one will be x1 bar, x2 bar, and this one will be x1. Right? So now, any concept will label these points, right? And they can label it in many ways. You can actually label it in 2 power 4 ways. You can call everything positive and everything negative. So, however, disjunctive concepts, if you are looking at only K-monotone disjunctive concepts, let's say here, for example, we are looking at 2 monotone disjunctive concepts. So, those concepts, they can color these in certain ways, right? So, one concept could call so one concept could label this as +1. Well, actually, let's do that. So we can enumerate all the possible concepts that there could be, right? One disjunctive concept could be something that calls everything positive. One concept could be which only calls those things positive which are x1 is positive, one which is x2, one that is x1 4. So you can actually just have 4 k monotone disjunction concepts, right? What you will see is that for each one of these examples, let's ignore this one. But for each one of these examples, you will be able to draw a line to separate them. So let's do that. So x1, right? So let's say this is our conjunctive or disjunctive concept. So this concept will call this 0, right? This will be 0, false, not part of the concept. This will be called true. This will be called true again, and this will be called false. Yes. Now what you will see is that you can draw a line like this, and it will separate the space into 2 parts such that all positive are here, all negative. Right? Is that clear? Okay. Now we can look at another concept. Let's look at the reverse side. The reverse side is also easy. x2. So thus x2, this will still be true in x2. This one will be true in x2. And these two will be false. For both of them, x2 is negative. That means you can draw this. Right? Now the third one is x1 over x2. Right? So in this one, all these 3 will be true. Only this one will be false. So that means you can draw a line like this. Right? So the point is that if you have a data set that is being labeled by a k disjunctive concept, k monotone disjunctive concept, then you can always draw a line that can differentiate between them. Okay? Which means, and that is the property that Winnow exploits. So Winnow, what it does is that instead of trying to learn these concepts, it tries to learn that line, because that's equivalent, right? Drawing a line is same as finding the concept. Okay? And in fact, without giving you the proof, I can tell you so if you have any concept, right, any k monotone disjunctive concept, then this line will be the line that will separate the two types of concepts. So now let us hark back to our days of Euclidean geometry, right? So remember the equation of a line in space. What is the equation of a line? Right. So of course there are many ways of expressing a line. So line. So as you said, let's say your line is expressed in 2-dimensional space, x1 and x2. So one way to express the equation of a line is what we call x2 is equal to mx1 plus c, right? That is basically this is the slope of that line that you have. That's one way. But the way that we in machine learning try to define lines as is this, as you said, is something w1 x1 plus w2 x2 equal to sum. Okay, these are the theta w1 w2 are all scalars. w1 comma w2 comma theta, they all belong to the real space, right? So that is the one way that we are going to express our line. Okay. So what k monotone disjunction says, so you can express a line in any dimensional space. So this is in 2-dimensional space, so this will look something like this. But in n-dimensional space, it will be what we call a hyperplane, but it will have same equation, right? So the idea is that if you have for let's say 8 dimensions, for d equal to d, okay? If you have a certain disjunctive concept, if your concept looks like this, concept is x1 or x3 or x4, right? So this is our concept. It calls anything which is in which x1 is positive or x3 is positive or x4 is positive as equal, right? So what that sort of relationship tells us is that the line that can be written like this, 0 x1 plus 0 times x2, 1 times x1 is times x2 x1 times x3, 4, 5, 6 is equal to half. This equation, that this line or this hyperplane in 6-dimensional space will divide the data very nicely. It will divide it in a way that all the positive points that are labeled by this concept are on one side and all the negative points are on the other side. In fact, you can also show that for any positive concept, right, 1 times x1 plus 0 times x2, x3, 1 times x4, so on, will be greater than half. And for any positive example, any example that is labeled as positive by that concept, for any negative example, the other less than. So it will be on this side of that. Okay, so remember, the reason we sort of express our data like our lines like this is a general discussion, is that any point that is on this line, right, will satisfy this equation. Okay? For any point on this line, this will be true. For any point that is on top of the line, this value will be greater than that. And any point that is here, it will be less than. So if W1 x1 plus W2 x2 will be greater than theta for this point, okay? W1 x1 plus W2 x2 will be equal to theta for this point. This is just down. And W1 x1 plus W2 x2 will be less than theta for this point. So suddenly now we see that lines are very useful. Lines are like a test for us to see which side points are lying on. And that kind of becomes a classified as well. So here, this is the equation of the line. So theta would be part of it, right? Given alright. If you have 2 points, right, you can learn the equation of the line, right? You only need 2 points to learn the equation of the line. So you can solve those two, right? So let's say you have 2 points, you can write it as this, these 3 equations, and you can compute all the items, right? So theta will come from what the line is, the del theta. Right. Of course, another thing you can note is that if the line passes through origin, then theta will be 0, because this point will satisfy this equation. W1 0 plus W2 0. Theta will be 0. Yes. Yeah. No, we are not defining the point. What we are saying is that there is a point here, x1, x2, and for that point, this is true. The point is always represented using 2 values, x1 and x2. Exactly. So it's basically maybe the thing that I learned. But the idea is that this point will satisfy this equation. This point here, x1, x2, will satisfy this equation, and any point on the line will always satisfy. See what I mean? Any other questions? Alright. So the point is that Winnow algorithm, what it does is it makes use of this relationship. It says that if the data is being labeled by a k monotone disjunction, then that means there is a line that differentiates these two types of points. So why not we learn that line or equation of that line? So when we say we have to learn the equation of the line, all we have to learn are these weights here. These weights, right? So we just need to learn the weights. And in the case of Winnow, we assume that theta is half because that's sort of a result that we get. Now, what I want you to do when you go back is try to figure out why this is true. Or in general, if you go to the lab, study. Why is this true? And you will see why this is true, right? Because the thing is that this is a k monotone disjunction, right? And all of those things that are in the disjunction are here, right? And if it is a positive point, that means at least one of them will be 1, right? That's why it's being labeled as positive. That is the That is the disjunction condition, right? The reason a point will be 1 is one of these values has to be 1. That means that even if the rest of them are 0, that will still be greater than x. And the same way around, if it is a negative point, which means it's been labeled as false by the concept, that means none of these are 1. Right? If any one of these is 1, then it will become false. So none of these are 1, that means none of these values are, all of these are 0, right? So it will be less than 2. See what I mean? So that is the reason why this relationship is here. Why monotone disjunctions are linearly separable. So now let's look at that. So I talked about this. So the idea is that whatever the concept be, right, as long as it is a monotone disjunction, you should be able to draw a line. And what line it would be is what Winnow will give. So this is the algorithm, right? We will not go into step by step of this algorithm too much. You will get a chance to play around with it. But the general idea is this. So it's a classic online learning algorithm. So the way it works is that initially it sets its W to all 1 because it doesn't know anything. Right? So initially it thinks that anything will be part of the concept. So in the terms of line, it is a line with this equation, right? And then as data comes in, it tries to make predictions. So remember, this is how it does predictions. Now there are some new terminologies here, which I'll keep using a lot. So you see this sign over here? This is just a transpose. So the one thing you need to understand, and I'm sure you do, is the notion of a vector product, right? So if I have 2 vectors, you can do a vector product. So if I have 2 vectors A and B, let's say A is A1, A2, and A4, and B is B1, B2, B3. In the slide you will see I mostly use a bold lowercase alphabet as a vector. Right? So a vector product, or also known as a dot product or an inner product, yeah, we do not have enough notation. So can be written as, we usually write it in many, A dot B, or we can write it as what I say, A transpose B. This is what I will use the most. And these are all equal to A1 B1 plus A2 B2 plus A3 B3. Right? That is the vector product. So you'll see this over and over again for the rest of the course. The reason I write it this is what the matrix notation is, right? So always remember that a vector is always a matrix with one column. A vector is a matrix with only one column. It's a column vector. So when I am trying to do A dot B, what we can do is I can take A and then I take a transpose. The transpose is just sort of making the rows as columns. So this is what we do. So this is B and this is A transpose. And when I multiply that in matrix multiplication, essentially what will happen is this will get back to this. Right? So that will be same as A1 B1 plus A2 B2 plus. So that is why in rest of this course, whenever I have to do a vector product, I will write it as A transpose B. Okay? If you are not familiar with this, I strongly suggest go back and brush up on your matrix vector algebra. Okay, any questions? So going back to this algorithm, all it does is it starts with certain estimate of my line, and then when a new data point comes, it makes a prediction. It sees if this data point x of I, is it on this side of this line or on this side of the line, right? And depending on that, it says that its prediction is this. Then it looks at the true label. The true label is this. And then if it has made a mistake, then what it does is it shifts its line. So it adjusts the line a little bit so that it is not making a mistake on that point anymore. And it keeps doing that until the data is done. Right? So that is a sort of an algorithm that you can actually implement. Okay? In fact, in one of the notebooks, I have that. Right, so if you go to the Winnow tab, yeah. Right, so you will see a short demo of Winnow. So here we are trying to basically show Winnow on data set which is defined in 3 aspects. 3 is the maximum, right? So this is our D, and this is, let's say, our target concept. So our target concept is disjunctive. It means it's going to call anything that's positive on the third one as positive, right? This is what we do. We create our data, all the possible data points you can have with 3 binary attributes, each of them, and then we sort of start thinking. Right? So if you look at this is sort of the initial circle. So this is, remember that we know what it does is that initially it says all my weights are 1, 1, 1. So this is the plane. Now in 3 dimensions won't be aligned with the plane. So that is my initial plane. So if you plot that plane, it looks like this. It's a little hard to see, but this is the plane that satisfies 1 plus 1 plus 1 would have, and then you might not be able to see. Here. So these are our 8 points, and this is our plane, right? Now some of these points are labeled positive by our concept, and some of these are negative. We don't know which one is right. So these are the green ones that are negative by our concept, and one is hidden behind that, and then this is our plane. Okay. So now what we want to do, what we know does is that it slowly sort of adjusts it. Now it gets the first data point, and for each data point, it will up if it is a mistake. So that this is basically the Winnow algorithm coded in 5 lines, right? So the idea is you get a data point every time you compute the dot product with your current weight vectors, and if it is greater than theta, then you say it is positive rather than negative, and then you check if you have made a mistake. If you make a mistake, you update your weights. You update your weights. If you do not make a mistake, then you don't, right? And the way you update your weights is the whole beauty of Winnow algorithm, which is sort of how it updates the weight. It needs to update the weight so that eventually you would learn the same plane as the one that would have distinguished the two types of form, right? So if you, when you get time, you will sort of see that, and at the end, you will see that it perfectly does. This plane, it's hard to see this plane, but I think it does what I can run. Right, so see, now this plane perfectly distinguishes the two types of points. All the red are on top, all the green are on the bottom. So that is sort of the idea. So you want to, it first starts with the initialization of the plane, which of course makes a mistake, right? There's one green point here. But then slowly, as data comes in, it keeps updating its data points. Okay? So now let's quickly look at what it really does there. Any questions so far? Alright, I know it's a little sort of too many things to look at, but you go back into the gradients. So the idea here is that when you make a mistake, right, you can make 2 types of mistakes. One mistake is a mistake on a positive example. That means you called something negative when it was positive, which is this one. And the other mistake is in which you called something negative and it was actually positive. So you call something positive when it was negative. So that is this. So in both scenarios, you're doing something different. Okay? What you're doing is, if you make a mistake in which you call something positive when it was negative, you call something negative when it was positive, you are bumping up the weights of everything that was wrong. Okay? that is what we call promotion. And when you make other type of mistake, you are just truncating the weights of everything that was won in that exam. That is called that elimination. The idea is that slowly it will sort of bump up the weights of some of the examples, and it will zero out the weights of some of the other features. Right? And at the end of it, it will be left with only those features which are part of your disjunctive concept. So that is why we call it winnow, because it starts with everything and slowly it sort of whittles down or winnows out the bad ones, and only is left with the ones that are part of the concept. So if you work this out for a simple example, you will see how it works. Right? Any questions so far? Yeah. Right. So the question is that is first of all is Winnow a continuous learning algorithm? Now remember that the data here is finite, right? The data is defined using D binary algebra, which means that you can only have so many. So it cannot go on forever. At some point you will have exhausted on the data. That's number one. The second one is it is an online learning algorithm, right? So at any point you have a weight vector, and you are updating this weight vector at every step. So it is online in that sense. It is not. It's not batch learning algorithm. It means that it doesn't have to have all the data in the beginning to learn. So it can stop whenever your data is done. So let's say in your training data set, you only had 3 data points, right, or 3 examples. It would stop. Other question yet? If it cannot separate all of them, I see. So that's a very good question. The question is, what if there is no plane that is there that will separate the 2 points, right? And the reason that will never happen is because we assume that these points are labeled by a disjunctive concept. That means that they are linearly separate. But if it is not true, then what we are saying is that your true concept is not part of your concept space, right? So then it will stop when the data is done, but it will not learn the right way because there is no plane to be done, right? That's a good question. So if you think of one particular example, right, which is not a monotone disjunction, but that's what we call an XOR example, which is data that is labeled by X1 or X. So it's only true if one of them is true. Okay, otherwise not. So in that case, what you will see is that these 2 points will be true. These ones will be false. That means you can never draw a line that sort of divides the 2, right? So Winnow will not be able to learn. But it is okay because that is not a monotone disjunction. Winnow is only guaranteed to work if the data is being labeled by a monotone disjunction. Because we know that if that is true, then there will be a line. Right? That's a very good question because that is going to take us to the next step for such class. Next. Any other questions? Yes. In the case of negative example, well, there could be other feature values which are not part of the concept, which could be one. Right? So negative example means that any feature which is part of the concept will be 0, but the other one will be 1. And we don't know that in the beginning. We will continuously do it. Right? Alright, I'll stop here because we are out of time. So, alright, I'll go on Wednesday.